Hello, my dear fellow researchers. I welcome you to a new session of my channel. Um, this is a new kind of tutorial, and we will start uploading because from last 1.5 years I was not even upload a single video in my channel because I was little busy in my research work. So before starting the session, I want to say that this is purely for students and researchers who want to start their research in electromagnetics and especially wave material interactions, and it is for educational use only. I do not mean any kind of commercial issues of these videos, so I just want to clear it. I hope you all went through my previous videos which explain about basic designing or simulation basics, how to work with coordinate, how to give a port, how to analyze the results, and etc, those basic things. So I am not going to discuss in detail about the project or in detail about the thing I want to show you, but I hope if you went through the previous videos you can design it by your own. And the basic thing is you have to spend your time, and you have to practice a lot. Otherwise doing such critical simulations which works in a proper platform like softwares like CST, HFSS, whatever tool you use, but the basic it's same. You have to use basic electromagnetic theorems and the Maxwell's equations to solve um, a media, but the computational technique is different. You need not about much worry about those things, those computational technique what these peoples are doing. But if you have the package like CST, HFSS, XFDTT, FICO, and many more, if you have any package you can design it if you have the basic knowledge. So let's start with our today's tutorial. So we'll discuss with negative refraction test using omega type metamaterial lens. Whatever the metamaterial unit cell you are using, you can implement it in a number of ways. So it is one of the application, and this is a realized result from a paper. So I will give you the reference. If you want to practice it, you can practice it. The thing is that you have to practice. The more and more you practice, the more and more you will clear your doubts. So let's go. This is the basic metamaterial material quadrant, you can say. The first one, the general materials available in periodic table, where we get a right-handed wave, forward wave, and then we have evanescent wave at this quadrant and also this quadrant, because here we are getting a negative epsilon, and here we are getting a negative mu. The both are available in nature, but somehow it's plasma and it's ferrite, and they have different theories. And the most important part is, now we call it as the left-handed material, where the wave propagates in a backward direction, and the Snell's law reverses, and also Doppler's effect reverses everything, whatever we call the opposite medium to the negative index material, we say. So if you want to know about the detailed theory, I will give you the references of the best books which people follow to learn about metamaterials and their theories. So you have to go through those books and materials if you want to clear your doubts so deeply. Okay, so I'm not spending much time discussing those things. So you can see these are the first structures designed when Penry and their group, also Smith, realized it practically. So these are the basic metamaterials. You have must a periodic spacing, and these are for negative permittivity, and these are for negative permeability. The spacing must be periodic, and you are getting a response. Then these are the practical views, you can say, and this is how people measure after designing or fabricating a device. So you must keep in mind, whatever you are doing in simulation, it must be as you are doing it in practical. So your device, your surrounding inside the simulator software must be as you are doing inside a anechoic chamber. Those who are new people who do not know about anechoic chamber, basically you must know that anechoic chamber is just a room where there will be no reflected wave from walls. There will be pyramidal absorbers like this, which do not reflect back. It absorbs the electromagnetic wave. So you must have to think like that. Your design must be like that, so that you can get accurate result whenever you are going to fabricate or measure something. So this is a few applications. This is one of the applications. You can use left-handed material to focus your source, since it is doing some negative index kind of thing. The wave, instead of going this way, it will go this way, and in fact you are getting a focus point here also. So you do not need to use a concave or convex lens to refocus your beam. You can use a flat left-handed material. These are the basic things. I will give you the reference of books from which I took the snapshots. And this is the side view of a pyramidal absorber. These are your materials or split rings or wire structures you are using to get negative effects, refractive index, and this is your input wave and this is your output wave, whatever you say. Then the basic circuit analysis. If you want to go deep into the unit cell design and its parameters, how current and between two wires the current is behaving, what should be the inductance and capacitance value, or what should be the circuit behind your structure, you can go through the books and make your doubt clear. This is a very simple concept. If you are having two wires, it must have to provide inductance, and also if you have splits, it is going to give you a capacitance. So it is generally performing a tank circuit, and it is making oscillations. Okay, it's a resonant circuit. So these are the basics, how you can design it, and you can analyze it. So also, while testing the unit cell inside a simulated environment or inside a practical environment, there are many kind of results you can have. The orientations plays a major role. This is a paper result from Smith and all. They made it experiment nearly about 15 years before. So according to your orientation, how you are going to use this unit cell in your project, accordingly you have to test it. Suppose you are going to project it in normal direction, you have to place it inside a waveguide like this. If you are giving it vertically, then you have to place it like this. Whatever, according to your practical application, you have to do the studies. This is the basic paper we will discuss today, how to design or simulate. It is from IEEE transactions from microwave theory and techniques. So this is for your educational purpose. I am not using for any commercial issues. So we will follow this paper, how they do the simulations, how people throughout the world work in complicated simulation procedures. It is very simple, it is not so difficult, but we have to follow. Okay, we have to practice. So this is the unit cell I will show you. Generally I had already a lecture before how to simulate and how to get the results of a unit cell simulation. There are many kind of techniques, one of them I already show you. So we will start with the omega type lens, unit cell. You have two wire structures connected with a circle which have a split here. So first you have to do the bigger one, the big circle having radius r1, then you have to draw another circle with radius r2, then you have to subtract the first cylinder from the second cylinder, so you will get a ring, and then you have to make a slab here and subtract it, you will get a split here. So select this midpoint, then design a brick here, select this midpoint and design a brick here. So designing procedure is already same if you have gone through those videos, or if you know the basic of designing things. So this is so easy. So I hope I will give you those parameters, and the paper have also. So this is the basic. This is one of the book by Gallows and Ito, the most popular authors. They described it very well, you can follow it. Also this is one of the books. So let's this is the basic things I will discuss in this tutorial. So now we will go to CST design environment. These are the basics, so I don't need to go for those things. So to save our lecture time, I had already designed it. I don't need to go step by steps. I hope you can do it easily. So to design this, I just first build a cylinder, then I build another cylinder over there, and I subtracted it. Otherwise you can directly build one single cylinder with inner radius and outer radius. The inner radius is R2 here, the inner radius, then I gave the outer radius as R2 plus W. W is the thickness of this patch. Then we have split gap width. You can directly build a brick here and subtract it from the cylinder. Okay, so then we have thickness of that PEC layer. You can see this is the thickness of PEC layer, you can put it away. Then this is the wire width. This you can keep it as same as this one. Okay, not an issue. Again, after designing the omega shape, you can see it. After designing the omega shape, I can transform it directly. We will transform it to backside at the substrate height. Then we will have another solid here, then you will rotate it 180 degree, then you have opposite orientation, both the omega will be in opposite orientation. So this is the basic cell. Okay, we will design it. So I am gonna use it in such a manner that the wave will strike the metal here. So that is why I am using two ports. They are at this end and this end, so I am collecting S11 and S21. If I am going to project in this way, Z direction, so I have to put it over here as I did in previous video in square splitting result. According to your operation, you have to give the ports and find out the results. Okay, so this is the basic design. I hope it is very simple, you can design it very easily. So this is how we do those design. Okay, so now we will go for results and discussion after running with transient solver and basic things, and you have to fix the port impedances to 50 ohm. It is not gonna make any difference to the result, more difference, but you can design it. So we must follow one thing, that we are always be in confusion that is it same in HFSS? Yes, it is not so difficult in HFSS or any kind of software. If you know how to design it, if you know the electromagnetic fundamental, if you know the free space, if you know the coordinates, if you want to spend your time, if you want to play with these things, then they will become easier to you day by day. So the design procedure is same in all softwares. Also you can make the boundary box as per your wish. I had already discussed, you can design and you can give frequency, background, boundaries you can control. So here I am using the unit cell boundary condition. I had already told you, in one direction electric and another direction I am taking magnetic, and I am taking it open. Also you can use the unit cell boundary condition or periodic boundary condition if you need, and for that you must have to use frequency domain solver in CST. Accordingly, if your package change, the things around you change. So I have the license, educational license of CST, so I am using those things, so it makes easy for me. So let's see the results. We have 2 ports, so we will get 4 S parameter results. So S11, S21, then S12, S22. Since it is a symmetric structure, S11, S22 must have to be same, S21 and S12 must have to be same. So I am seeing the 4 results at a time. So first you can see the phase, the linear, then in decibels, real part, imaginary part, everything, whatever you want, you can use this 1D plot mode. And the crucial part is deriving the material parameters like permittivity and permeability from those curves and those curve data. So it is also not difficult. You have to export these plot data as as you know, ASCII file available here. So you can direct export plot data as ASCII format. So you can export it, then you can use it in MATLAB or any kind of plotting tools, or also you can use the template based processing of CST. There are many methods, so you have to use Nicholson's-Rossware NRW method to design your things, to derive your permittivity and permeability curve. So from that curve you can make sure that in which area your device is working, or your unit cell is giving negative epsilon and negative mu. Accordingly, the refractive index, everything you can see. I'm skipping that part because it is going to take a lot of time if I will do this. So if you are interested, you can follow it. Lots of paper are available, lots of theses are available explaining those things, how to derive those parameters. Okay, so also this is the basic analysis of the unit cell. So after you designing the unit cell, you have to assemble it in your project. So as I told you, our goal is this one. We have to design this device to test whether the designed unit cell is acting as a negative index material or not. So it is one of the applications. So let's go to directly the project, assemble project. I had already done it to save our time. So I hope it is not so critical, you can design easily. So I am explaining one by one. First I designed the PC materials. I named it absorber. Sorry, it is not absorber, it is PC materials, perfect electric conductors to you can see it from here. PC, you can see material, yeah, material 2. I gave it to PC properties. Okay, perfect electric conductor properties. So first I designed these two. So you must not worry about these things, like I made a taper here. You can directly just put the square here, no need to do the taper. Okay, also it is not so easy. Find out the coordinate points, like this coordinate, and these two coordinates. Directly use those coordinates and just define a curve polygon. You can directly use XY points here to design this and this. So these are not so difficult. Then I just make copy paste of the designed unit cell. so I must say you that it is not so difficult. You just copy from this window, paste it in this window, and just transfer it and make a copy. So just use the transform button, copy, then repeat it according to your coordinates. Okay, so whenever you are going to design a complicated thing or a multi-element thing, you must know your coordinates. You must know where you are now. Means if you are doing some design, you must know where is the origin and where you are pasting the thing, and where you are copying. All those things you must know, and layer by layer I just copy and paste those things. Those unit cells I just copy and paste. I just reduce to make a prism like structure. I just reduce the number of unit cells in layer by layer. You can see here I just reduced 2-3 unit cells in every layer, and I just made this one. So it is not, if you will zoom it, you can see here is one unit cell and I have the substrate in between, and another unit cell I have substrate in between. So accordingly you design it. Okay, after that you select these two words and give a waveguide port. So this is my design, so it is not so difficult. After that you can go for frequency. I just simulated it from 6 to 16 to show you in which frequency my unit cell is acting as a negative index material. First you design the unit cell, derive this permittivity and permeability curve, then you can get a particular frequency where your unit cell is acting as a negative index material. Then you implement, then you test, then you will see that at the particular frequency where your unit cell is acting as a negative index material, at that frequency you can see the bending of the electric field, as I will show you just now. So my design is ready. I just modified the background. I just want to see how the electric field flow. So I know that my field will flow like this and then it will bend, so I just make it like this. So you can extend it and see, make a large space, but your meshing will be too high. So higher the meshing, higher the simulation time it takes. So it is now 23 lakhs, so it will take half an hour approximately. I have a 120 GB system, a system with 120 GB 128 GB RAM, so it takes 15 to 20 minutes. If you have a laptop of 4 GB or 8 GB RAM, then it may take 2 to 3 hours or more than that. So accordingly you design, you simulate. If you want to reduce your simulation time, you go to global mesh properties, and you can change the mesh per wavelength, number of lines per wavelength. If you will reduce it, the number of mesh cells will reduce, but your result will become less accurate. So it is better to keep it in between 7 to 12 or 14. So you just do it and then simulate it as usually you simulate. All the conditions are same. Use the transient solver and then get the results. So I just directly will show you the results. Generally from my experiment I got that the unit cell is giving negative index at 13.5 gigahertz. So at that particular, we all know metamaterials are narrowband materials. It gives a particular parameter at a particular frequency. Generally it is not a wideband material, so the negative frequency we are getting is at a particular frequency. It is not a broadband kind of thing. So I just will show you few things, like here you can see the electric field simulation at 9 gigahertz. I will see you show you all of them. Okay, starting from 16.5 to 15, I will show you all the electric field simulations I collected here. So generally we consider the near field simulations while examining the negative refraction or all the metamaterial kind of things, because generally we can calculate the far field from the near field, and we can guess how will be the far field from the near field. So this is at 6.5 gigahertz. You can see the wavelength is large, it is not even passing the material. So at 7 it is just started passing the material in then at 7.5 it enters to the material. Gradually it start passing the material, the wave, sorry. And at 9 gigahertz it penetrates, but the field is distorted. As usually I told you, it operates at a particular frequency. So at 9.5 gigahertz you can see it is bending the wave, but the field is distorted at a lot. Then we go to 10 gigahertz. You can see the wave is coming like this, and it is bending straight away 90 degree towards it. The main lobe will be towards this, you can see. Then at 10.5 gigahertz, the same kind of thing. You can change the view here, the volts per meter, you can visualize the things clearly. Okay, now at 11 gigahertz you can see the wave is coming like this, and again it is passing. 11.5 you can see the wave is coming straight away, it is going towards this, and gradually it clears that it is making something negative refractive index. At 12.5 you can see even at 13 and this is actually our point. 13.5 you can see exactly the wave is coming, and it bending like this, as I saw you in these previous results, sorry, in discussions, as I told you. Okay, now it is at 14, is at 14.5 and this is at 15. You can see directly the wave is clearly penetrating and going straight forward. Okay, there is no negative refractive index at 15, not even at 12. So it is working fine at 13.5 or around that. Okay, 13 and 13.5 or near about 14. So this is the basic result of a metamaterial pyramidal lens to see the negative index. So as this add-on, it is very easy, and if you are spending time, it is not so hard to do. If you will see the far field results, the main lobe is you can see the device, and the main lobe you can directly see from here. You can see the far field results where the far field. Okay, you can see the structure is here. The far field is particularly going towards this file at 15 gigahertz. The far field is straight. The main lobe direction you can see from the polar plot. The main lobe direction is towards 90 degree if your device is here. Okay, you can change the properties. You can see it. So we saw the near field and far field manipulation of a metamaterial lens designed from a omega shaped unit cell. So I hope you enjoyed this video. It will help you in your research work, and these are the basic references you can use to study these kind of things. So I took these references from the papers, so you can follow these things. You can do a lot of things, and if you want to contact me, you can contact, but please do not ask silly questions. Those questions you can do by your own. So I do not have much time to address all the fellows. Even I'm taking classes, even I have project works and maybe PhD work, lot of works are there. So sorry for those I could not reply you in time, but if you are really interested, so address your problem properly and do not ask silly questions, and if you have any doubt, go through the previous videos. I hope all your doubt will be cleared for designing and modeling kind of things. If you want to do something new, if you have a concept and you don't know how to design it, then you can ask me if you want. So thank you for today. We'll come with a new video or with a new concept or new idea to solve your doubt as soon as possible. Thank you.